Swayam Prabha. Digital India. Educated India.
So we welcome you to the second session on monitoring and fault diagnosis. The first talk is going to be on dynamic data reconciliation using conditional dynamic variational autoencoders with particle filters to enhance process monitoring performance. It's going to be a virtual talk, and yeah, with that note, let's begin.
The chemical plane. First, at the beginning. Hello everyone, my name is Zhou Guanshen, and I am a graduate student from Taiwan. Today I want to present how to enhance the monitoring performance of the process through the data-driven conditional dynamic variational autoencoder combined with the nonlinear data reconciliation method of the particle filter in the chemical plane. First, at the beginning, let's discuss what is the use of the measurement data in the industrial process. In a chemical plant, various processes can measure many values through a sensor, such as flow rate, temperature. And this data can usually be used for process safety, quality monitoring, or process control in the factory. Therefore, the quality of the measurement data will directly affect the performance of the monitoring or control. For this reason, the more accurate the data is better. However, the reality is usually not so smooth. So data reconciliation and filtering have been proposed in the past to eliminate noise. But most of the methods proposed in the past assume that the model of the process must be known and the process disturbance or sensor noise are known, or a linearized model is used. So these assumptions are difficult to realize in the actual industrial process. Therefore, the data-driven model has been widely used recently. Although the process model can be established without a strong knowledge background, its shortcomings are also obvious. That is, when the quality of the training data is poor, the model will be mismatched, and the prediction will be inaccurate. So the monitoring will not be accurate at all. And then why is monitoring will be inaccurate can be explained with a simple example. And this is a CSTR simulation process, and this right side is a control value output and the monitoring result. This can be seen as the output of the output layer have the serious noise, and the controller obviously does not change when the sampling time is 100, but the output conditional have to be changed, which theoretically mean the process is abnormal and need to be monitored, but is not detected because of the too much noise. On the other hand, the output noise below is relatively low, and abnormally can be detected when the time exceeds 100 on the monitoring. It can thus be demonstrated that higher quality measurement data lead to better monitoring performance. Therefore, there are several key issues to be addressed in my proposed method. The first and second point are nonlinear and dynamic problems in the process, and a suitable data-driven model framework should be selected. As for the noise and abnormal data at 3 and 4, we hope to eliminate them as much as possible by combining filter. The reconciled data will be able to further enhance the performance of the process monitoring, because the influence of the sensor has been avoided as possible. The method I proposed will change the conditional variational autoencoder model into a dynamic model, called CDVAE, and will be used as the best model of the particle filter Finally, the results of the reconciliation will be monitored with the CDVAE model to test the proposed method. How to perform monitoring and the overall process can be roughly divided into two parts. The first part is the pre-training of the CDVAE model. We can carry out the CDVAE modeling by correct the input, that is MV, and the output PV data of the closed loop process in the industry. The established model with the parameter can be used for data reconciliation through CDVA EPF when it is applied online. And the reconciled data will be applied at the monitoring. Of course, not only monitoring, but reconciled data can also be applied to control. The CDVA I proposed is also a probabilistic data-driven model. It's very similar in structure to the VAE, and it will project the data into the latent variable space through the neural network and let the generate latent variable follow the Gaussian distribution, where the output of the encoder and decoder is the mean and standard deviation. And because the chemical process is dynamic process, the encoder part is replaced by RNN and dynamic neural network to solve the problem of the dynamic data. In the general common data dynamic state space model, it can be expressed as the transition and emission function. X is the input of the process and Y is the output of the process. Under this data-driven model, the proposed is to predict the distribution of the Y more accurately given X. Therefore, we can write the objective function like this: maxima Y given X, and we can derive it through Bayes' theory. The derived conclusion is expressed like this. The orange part is KL and the green part is reconstruction. When we have the model structure, we can train the CDVAE model well. How can we use particle filter well in the future? The method of the particle filter is generate many particles and predict through the transition function, which just corresponds to KL in CDVAE, which is also function for prediction the next time point. The prediction latent variable space will be reconstructed back to the original space through the emission function, and this corresponding to the reconstruction. And how to solve the problem of our outlier? You can see the KL. For the simple monitoring, if the value of the KL have a large change or a peak in the instance, we can consider it to be an error phenomenon caused by sensor. At this time, the major value will be replaced by the result calculation by particle filter. So let's sort out the overall process here. For normal noise data, we collect the data at the beginning, project it to the Z through the RNN encoder, and reconstruct it back to the original specs through the decoder. The part friend in the blue will perform particle filtering to obtain the reconciled value. And this value is our clinical data. After replacing the original data with this data, it will be reprojected to the Z through the RNN encoder. In KL, we can carry out the process monitoring. So what if the data has the outliers? We project the data into the latent variable, but at this time, the monitoring specially used to detect outlier will find that the current data is abnormal. So when the data is reconciled by particle filter, it will additionally replace the data first. At this point, the data has undergone additional outlier reconciliation. After that, I thought it should be the same as normal data. So at this time, the CDVAE PF of the normal process will be executed again, and it will go to Z through the RN encoder. After filtering, it is reconciled, and this value is used for monitoring. So far, my math has been explained. Here is a numerical example of the closed-loop CSTR is used for simulation. And since the problem to be solved by my math, I propose including the reconciliation of our outlier. I will add the large random noise to simulate the outlier situation in the data every 25 sampling time. And then, in order to verify the monitoring, I will gradually adjust the physical parameter of the FCSTR function when the sampling of the test data exceeds 100. Here is the schedule of model training. The training data has 2,000 sampling. You can see that the blue part is the measurement value with outlier. So there will be many peaks in the data. And the test data has 300 sampling and also have outliers. Here you can see the KL and the reconstruction standard deviation. And there are many peaks in the data point with the outlier. It means that the data needs to correct it. As you can see here, I gradually modify the parameter when the sampling time exceeds 100. So the KL monitoring and the standard deviation greatly reflect to the abnormal situation. By the time of the sampling point 20, the model prediction has even deviated seriously. That is because the operating conditions have been completely different. So it is a normal phenomenon. At this point, we reconcile the test data. This is the animations of the actually reconciliation process. We can see that we have the correct the outlier back to the normal range step by step, and the value of the corrected data in KL or standard deviation has also returned to normal. We can compare how the results different before and after. The blue light is our measurement, and the orange light is the result of the purely just using the CDVAE, while the red light is the result of the pure using particle filter absent the model is known. And the black light is the CDVAE PF. So, and the green light is the real value without noise. The CDVAE of the orange light is be biased by the influence of noise, and the red particle filter will be due to the problem of the particle weight deviation. So the prediction value may deviation after the passing the outlier. When the math I proposed from the present of the MAE has also made great progress. By the way, because of the operating conditional behind the test data abnormal, MAE only calculate the first 100 sampling point. And the monitoring of the KL using the CDVAE alone, it is only when the sampling point in the closer to 200 that the situation of significant is set to the control boundary occur. However, after the reconciliation of the CDVA PF, the monitoring is obviously beyond the limit at about 180. And in addition, since the outliers are all resolved, the misjudgment situation is also reduced during the monitoring. Therefore, the method I proposed can indeed reduce the misjudgment caused by the sensor abnormal and detect process abnormal early. The result just now is the simulation results of only one model. Here I have repeat the test CDVA PF 35 times. We can see the amount of the 35 results. The median of the MAE using only CDVA is about 0.157, while CDVA PF dropped to the 0.13. Another test in the 5 outliers before the data 150. How high is the probability of the being detected? So we have the 35 model, and there are summed and averaged as a ratio. And about 97.7% can be detected and correct the outlier. Finally, in monitoring, we can use the FDR to quantify the result. FDR means that when the process is abnormal and the monitoring indicator also show this abnormal condition. And the closer the value is to 100%, the more accurate the monitor is. So in the text, the model has obvious abnormals after the 150 sampling point. So the FDR monitoring is established after the 150 point. So it can be seen that the FDR of the pure using CDVA is lower, only close to the 40%, while the CDVA PF is close to 70%. And here is the main math test using the industrial data, which is the distillation tower process. And the purification of the EDC is the main purpose of the distillation tower. For the modeling variable, I have the 13 process variable are selected, including feed flow rate, temperature, and pressure. The output of the model is the top tower temperature of the distillation tower. So the training data has the 800 sampling points and the testing data using the 2000 points. This is a result of a reconstruction compared with the original measurement data or simply using the CDVA model. It can be seen that the CDVA PF of the backlight has indeed reduced the range of the noise. From the result of the KL monitoring, it can be seen that due to the elimination of the noise and correct the outliers, the situation of the misjudgment on monitoring has been significantly reduced. And finally, let me summarize the math I propose. The first part is the CDVAE model, which is the particularly suitable model for the chemical engineering process with the dynamic and noise. The second part is that I judge and reconcile the outlier in a reasonable way and eliminate the negative effect of the noise and outlier. And finally, the reconciled data can be directly used for process monitoring under the framework of the CDVAE model. And it can also be seen from the test case that I proposed the math really improve the monitoring performance. This is the end of my presentation. Thank you for your attention.